thanks a lot for the very kind. First of all, for the invitation. I'm generally speaking big supporter of initiatives driven by young people, so it's really a pleasure, and for the kind introduction, of course. So okay, I kind of designed this talk to be very broadly accessible to a whole physics audience. So I hope you will not get too bored if you're too specialized. But yeah, in that case, let me know. We can perhaps speed it up and focus on the last part. All right. So the talk, as Thomas mentioned, so the talk is about quantum simulation, right? So this is kind of a rapidly developing field. And yeah, so in the first part, I plan to give as I said, a very gentle introduction to this core idea, right? And so I want to discuss why quantum simulation is believed to become an invaluable tool for scientific research today and even more so in the near future. And in the second part, instead, I plan to discuss some recent progress in this direction, particularly done within our group. Okay, so let's start. So let me refresh. Let me give refresh our ideas on simulation, right? Because that's what we would like to introduce a new paradigm, right? So generally speaking, simulations are necessary. Why? Well, because we can't solve a model exactly, right? So typically, we're only able to solve a mathematical model in some simple limits, right? Which is nice. We can gain some insights, but we need to resort to simulations to understand the more complex predictions of the model. So let me refresh how this happens in the context of classical mechanics, right? So basically, one of the early drives that led to the development of quantum mechanics is planetary motion, right? So as we all know, the motion of a single planet orbiting around the sun obeys Newton's equation, right? This can be explicitly solved, and this elegant solution explains much of the astronomical observation, right? Now, however, when we consider a system of many celestial bodies, right, called n their number, we deal with a system of n coupled Newton's equations. And first of all, this problem is famously non-solvable, even for n equals 3. So what we can do is performing a brute force numerical computation of the trajectory, so numerical integration of Newton's equation. So essentially, we have 6n variables, all the positions and velocities of all the bodies, right? And we can use Newton's equation to update these variables over short time steps and repeat this procedure over and over to obtain the full trajectory, right? Now, with modern computers, this can be done very efficiently for thousands or maybe millions of bodies, right? So it's fair to say that brute force numerical computations are extremely powerful. Now here, I don't know if it's no, sorry. Okay, why is it not starting? It has started. Okay, so here on the slide, so you were supposed to see an animation of a complex animation of an n-body gravitational problem that you can obtain by numerical simulation. Now, of course, if we're interested to describe the structure of the universe over larger scales, we still like to have some simpler, effective description, right? But in any case, it's nice that we can always resort to and compare to numerical simulations. Now, let's move on to quantum mechanics now, right? So, likewise, one of the early drives that led to the development of quantum mechanics is the problem of the atomic spectra, like for example, hydrogen atom. And as we all know, the motion of a single electron around the nucleus obeys Schrödinger's equation, which can be explicitly solved. And this elegant solution explains much of the observation in atomic physics, right? So far, so good, right? However, we meet some bad news when we move to the corresponding many-body problem, right? For example, a system of n electrons. Now, of course, this problem is non-solvable, even for n equals 3, just like the classical case, so nothing new so far. But there is something much worse going on here, right? The point is that the Schrödinger equation describes the evolution of the n-body wave function, right? So what is the n-body wave function? Basically, it assigns a complex number for every possible configuration of the n particles, right? So the amplitude of the wave function. So basically, that's the crucial point. So the number of parameters that we need to describe the system blows up exponentially with the number of particles and or with the evolution time of the system, right? So even if you start with a simple wave function, for example, an uncorrelated wave function that you can describe with relatively few parameters, this will, in general, the complexity will increase in time, and in general, you will meet this exponential wall. So basically, you can quickly convince yourself that this problem is real, right? So basically, this exponential blow up of the complexity becomes rapidly impossible to handle with any conceivable classical computing device, right? So you can quickly convince yourself that this problem is real, basically by making an estimate, a simple estimate for a problem of interest. So here, basically what I did, I reported for you an extract of the Nobel lecture by Walter Kohn, right, where he even uses this argument even to provocatively argue that the many-body wave function is not a legitimate scientific concept, right? So the essential point is that the amount of information that is encoded in the state, say, of 1,000 electrons, right? This amount of information easily surpasses the amount of matter in the entire universe, right? So this bottom line here is that the brute force computer simulations of quantum many-body problem is fundamentally out of reach, right? As a matter of principle. So it's not just that we don't have good enough computers today, but maybe tomorrow we will have, right? So this is really it's really a limitation of nature. We will never be able to perform a brute force simulation of the quantum many-body problem, right? And this is why if you Google quantum many-body problem, in contrast with the previous nice images, essentially, that you've seen on the slides, you just see a bunch of funny and incomprehensible drawings invented by theoretical physicists. But this is because it's even very hard to visualize quantum many-body motion, right? It's just too much information. So basically, quantum many-body theory calls for all sorts of approximation schemes and phenomenological theories, which many of us spend their life on, right? Okay, so there is this fundamental bottleneck, but maybe before going on, it is legitimate to wonder, essentially, why would we even bother about this problem, right? So after all, for example, if we consider a football, right? So this is made of, as far as we know, of many interacting quantum particles, but arguably we can predict its behavior extremely well, even without having to solve the quantum many-body problem, right? So are we really sure that this is an important problem? Well, the point is that many important phenomena that we care about are intrinsically quantum and intrinsically many-body, meaning that ignoring quantum effects or ignoring quantum correlation effects are bad ideas, so they miss something fundamental about the nature of the problem. And let me just flash some relevant examples, right? So for example, in the domain of chemistry, it would be very important, for example, to have first principle computations of molecular structures and reaction rates, right? And in some cases, quantum effects are believed to play a fundamental role here. Of course, the computation of, for example, of the ground state energy of molecules is a computation that requires fundamentally quantum mechanics, and this is important to get precise estimates, but also some of the phenomena are believed to be inherently quantum mechanical. So I think, I'm not an expert in this domain, but I think photosynthesis is one of the examples where people believe that the coherent electron transport across these biomolecules, these light harvesting complexes, is really playing a role. Okay, another domain where this is the quantum many-body nature of the problem is supposed to be important is solid-state physics, of course. So there, first principle computation of the quantum many-body problem would allow us, in principle, to have first principle computation of material structures, for example, or non-equilibrium responses of materials, and this would be important, for example, to have to predict new materials or to predict new behaviors of matter, or to understand better certain elusive phases of strongly correlated electrons, like, for example, high temperature superconductivity and so on. And of course, even here, the applications are rather relevant, right? And even in the context of high energy physics, for example, first principle computation of the quantum many-body problem would be important in nuclear physics. But even, this is something I will touch upon later in the talk, even this would allow us to have a first principle computation of the behavior of matter under extreme conditions of temperature and pressure, which are believed to happen, for example, only in the early universe evolution, or in the inner of heavy stars, or even in heavy ion collisions at modern colliders. Okay, and this here I listed some problems coming from the natural sciences, but actually there are more reasons coming from outside the natural sciences to believe that solving the quantum many-body problem is useful. Right? So one famous example being Shor's factoring algorithm, right? Which has, as you probably know, very important consequences in cryptography, so in everyday life, actually. Okay, so there are several reasons why this problem is more than interested, both inside science and outside of science. Okay, so to summarize, the state of the art is that solving quantum many-body problem would lead to a huge progress in several branches of science, as I argued. However, brute force numerical computations are fundamentally impossible, fundamentally out of reach, as I described before. And then controlled approximation schemes, of course, are not infinitely powerful, so they suffer in many of the interesting cases we care about. And phenomenological descriptions are sometimes not completely satisfactory, right? So this seems like a bad situation. And the question is there a way out? Is there something we can do about this problem, right? And one possible way out was suggested by the famous physicist Richard Feynman, that we all know, right? So basically, Feynman's idea was the following. So the point is, if we can't process a quantum many-body wave function in a classical device whose units can only be in two states, right, 0 and 1, so the point is, why don't we process it using a system of individually controlled quantum particles, like atoms or photons or electrons? So the proposal essentially is that we will never be able to encode the many-body wave function, say, of 1,000 electrons in the universe, right? But we may be able to encode the wave function of 1,000 electrons if we had a controllable system of 1,000 atoms, for example, right? And if we learn how to efficiently manipulate these atoms, then we may carry out computations on the many-body wave function using these atoms instead of using a computer. And this is basically the fundamental principle of quantum simulation. Okay, so point is, how do we implement this idea, right? So how do we simulate a quantum system using a quantum machine, right? So the most important thing that we need is a new type of hardware, right? As I said, this is the crucial difference, right? We need a hardware. Essentially, this should be a quantum many-body system which we can control largely or fully. So ideally, we should be able to freely manipulate its units, but here comes the crucial point, without somehow without affecting its quantum mechanical functioning, right? So in this way, we can encode the degrees of freedom of the actual system we are interested in, so your favorite biomolecule or material or nucleus, we can encode it in the hardware degrees of freedom, right? Which may be atoms or photons or electrons, whatever you can efficiently control in the lab, right? So this is the point is basically building this kind of connection or bridge between the system of interest, the system you would like to simulate, and your controllable quantum hardware. All right, so suppose you are given such a system, right? Suppose you are given a system of controllable quantum many-body system on which you have a good degree of control, maybe not perfect. So what do you have to do to implement Feynman's idea, right? Well, first, you have to devise a mapping between the states of the system of interest and the states of our hardware, right? So basically, we want a correspondence between the Hilbert space of the system, the degrees of freedom, and the Hilbert space of the hardware. This mapping may be more or less obvious, right? It doesn't matter as long as it is a mapping. Okay, so this is the first ingredient. Second ingredient, we need to be able to prepare our hardware in the particular state that corresponds to the desired state of the system. So typically, for example, the ground state of our strongly correlated Hamiltonian, right? This may not be so easy, but that's part of the task. Third, and this is usually the first bottleneck in this implementation, is that we must be able to tune the interactions of our hardware, right, such that its evolution corresponds to the evolution of the desired system. So the interactions are described by a kind of Hamiltonian. So our hardware has some native interactions, some native Hamiltonian, and we must be able, what we need essentially is to tweak the hardware Hamiltonian in such a way that it reproduces the forces, the Hamiltonian of the system of interest, right? So this is not easy also in principle. And finally, we need to be able to measure observables in the hardware that correspond to the observables we care about in the actual system. So basically, this is, if we are able to carry out these steps, this builds up a complete correspondence between the quantum evolution of our controllable hardware and the quantum evolution of the system we care about, right? So in a single equation, we are establishing this equivalence, right? And this is what we must be able to do if we want to overcome this exponential wall, this exponential bottleneck of classical computers. Okay, and of course, this doesn't look like a very easy problem, right, in general, right? So if you want to simulate a complicated biomolecule or some complicated material or quantum chromodynamics, right, you want to incorporate this in some atoms that know nothing about it. They just want to have their own forces, and then they don't know about your problem, right? So it is a very complicated problem. All right, so basically, at this point, I hope I convinced you that this is something extremely interesting to think about, actually, this original vision by Feynman, right? And of course, it would be great if this beautiful theoretical idea can be actually implemented, right, with actual degrees of freedom that we can deal with in the lab, right? So what is the state of the art in the realization of such a hardware, right? So there are several competing experimental platforms, right? So basically, we can roughly categorize them into the main ones, I would say. You can categorize them into families, right? So on the one hand, we have the so-called AMO family, the atomic molecular optical systems. And on the other hand, we have solid-state systems. So typically, we think of the first one, the AMO family, we think of them as analog simulators in the sense that they can naturally be exploited to mimic some of the physics of interest. I will give you some examples in the next slides. While typically we think of solid-state systems, so typically superconducting qubits is the most somehow advanced technology we have nowadays as implementing some digitized evolution. So what people like to think about when they talk about quantum computers, right? So I will be in this talk. I will not be very much concerned about this distinction. So I will focus mostly on quantum simulators in the sense of quantum platforms functioning in analog mode. Okay. Now the point is, what is the main difficulty? So the main difficulty is that basically all presently available platforms are quite severely limited, right? Severely limited in A, in system size, and B, in coherence time, right? So roughly speaking, the systems, you can roughly say that they lie at the boundary of classical computers. So what we can do with the most advanced somehow platforms that people can have nowadays in the lab is comparable, roughly speaking, to what we can do with our best classical computers nowadays. So this is because the technology to scale up the number of units in the systems and especially to keep the level of noise, so the environmental influence that are detrimental to the quantum mechanical evolution and functioning, this is very difficult to somehow to scale the things up in such a way that the noise is under control. And this is kind of in the course of development. So there are many proposals and many people are working on this. Now, for these reasons, essentially, this kind of presently available devices have been termed noise intermediate scale quantum devices, or NISQ devices. Now, of course, the holy grail in the field is the development of something called a fault-tolerant application scale quantum device, right? So, or FASC, if you want an acronym, right? So, in this case, basically, the idea is that we can digitize evolution and especially have level of noise that is so low under threshold that one can perform efficient quantum error correction. And in this case, in principle, one has an ideal universal quantum processor. Now, of course, this is the holy grail. It's not coming tomorrow, definitely, but ultimately, many people believe that this will be somehow the eventual route to being able to solve the quantum many-body, solve in the sense of simulate, of course, the quantum many-body problem. Okay, now of course this needs a lot of investment of time and of resources. So in the talk I will mostly focus, as I said, on on atomic molecular optical platforms, right? So I will now essentially sketch a few of this, the functioning of a few of these platforms, right? Just to give you an idea of how, basically, what I was mentioning before, how one can exploit the native interactions of the system in such a way to encode the desired degrees of freedom and the desired Hamiltonian evolution in a system. Okay, so and this kind of dictionary, this kind of mapping can have a higher sort of an increasing level of abstraction. That's my main message in the last in the next slides. Okay, so let me basically flash a theoretical physics perspective on the development of this platform. So the first, somehow, historically, the first, what you may call the first proper analog quantum simulator, historically was the so-called optical lattices, right? So basically, optical lattices mean that we have atoms that are cooled down to extremely low temperatures, and they propagate in a potential that is shaped by light, basically by shaped by laser light in such a way that this light forms an effective potential for the atoms. In particular, if you use counter-propagating lasers, you have basically standing wave potentials that form a periodic potential for the atom. Effectively, the atom perceives a periodic potential. So effectively, what we have is basically particles that are moving across a potential that looks like an egg box. An egg box, right? So basically, jumping across local minima that form a regular array, a regular lattice, right? And this looks very much like the kind of Hamiltonians we are used to in solid-state physics, you know? So the kind of Hamiltonians for tight-binding electrons in a crystal structure, right? In a crystal created by nuclei. Except that this system has nothing to do with electrons in a solid. So these are just very cold atoms that are tunneling through potential barriers created by laser light. So it's really an analogy. So in this sense, you can think of this as an analog simulator. And the level of control on these systems has become really high. So this picture actually is quite old, coming from Bloch Lab. But you see here that what the experimentalists can do is really place atoms in predefined geometries on the lattice, right, and form predefined. So this is just to show the level, the great level of control that can be achieved. You know? So you can displace atoms in particular shapes and essentially engineer the initial state and engineer their dynamics. So as I mentioned before, the model Hamiltonian that describes this kind of systems, once you describe it in a tight-binding approach, so essentially as looking at the evolution of particles in the low-energy description, this looks very much like the Hamiltonians we're used to in condensed matter physics. So we have basically a Hamiltonian that consists of a hopping term, right, for particles that jump across the local minima of the potential, which if you use in the geometry that I mentioned, so for two counter-propagating lasers in two perpendicular directions, this becomes just a square lattice. And then we have interaction terms that originate from the native interatomic interactions, right? That can also be tuned by other experimental tricks. So basically, we have a sort of so-called Hubbard model or Hubbard Hamiltonian, which can be a Bose-Hubbard or a Fermi-Hubbard, depending on whether your atoms are fermionic or bosonic, right? And again, the time scale, the spatial scale, the length scales, and the time scales are completely different from the ones that we have in solid-state physics. So these are very slow and very large systems, so we can efficiently image the dynamics of these particles. So it's a completely different system, but there is a kind of mathematical mapping or mathematical analogy to the Hamiltonians that we would like to simulate, for example, in condensed matter. So as you may know, this kind of Hubbard models are thought to be somehow the fundamental models that describe strongly correlated electrons in cuprates, for example. So this kind of development of this kind of system is thought to ultimately lead to cracking the mysteries of this kind of high temperature superconductors. All right. So and then we have, as I mentioned, we have an increasing level of abstraction in the mapping. There are all sorts of clever tricks that people invented to realize to enrich the toolbox and realize richer and richer families of Hamiltonians, right? So one example is, for example, if you use speckled patterns for light, you can realize quasi-random potentials. And this was realized, for example, in Alan Aspect lab in Paris to study Anderson localization. Again, this is Anderson localization of ultra-cold atoms in quasi-random potential created by light, right? So this has very little in common with physically in common with the original description of Anderson localization for impurity bands in semiconductors, except that there is an analogy, right? So this is an analog simulator of the original Anderson Hamiltonian for alloys. Another trick that people developed or invented is associated with the fact that you can shake the lattice periodically, right? And because of this periodic shaking of the lattice, essentially you can engineer effectively the phase of the hopping, right? So the hopping acquires a complex phase, right? Which is associated with this effective shaking of the lattice. And this amounts to having an artificial magnetic field. So these are neutral particles. These are neutral cold atoms, so they don't really feel actual electromagnetic fields, except that with this kind of tricks, you can engineer a synthetic magnetic field, right? And in this way, people managed to study phenomena like dynamical localization or quantum Hall effect or chiral edge states and this kind of physics. Another interesting approach basically used internal spin states. So basically, you can use atoms that have internal spin states, and this internal degree of freedom can essentially be used as a synthetic dimension, so as an extra dimension on top of the spatial dimensions of the system. And this was used in Florence to study again some versions of the quantum Hall effect. So you see, this synthetic dimension, I think, is a particularly interesting example of how the encoding of the system of interest can be quite abstract, right? So you can realize a mapping that has some level of abstraction in the hardware degrees of freedom. But as long as there is a Hilbert space correspondence, Hamiltonian correspondence, observable correspondence, and so on and so forth, then the mapping goes through, and you can use this to effectively simulate or mimic the desired natural system of interest. Good. And of course, eventually, I think the grand goal of this program is to realize sufficiently cold fermionic systems such that they reproduce strongly correlated physics that is thought to underlie the physics of materials. For example, the high temperature superconductor phase of cuprates that I mentioned before. Okay, so this is one, probably historically the first platform that was developed. Now there are other platforms that are acquiring a lot of traction recently. So one that I wanted to mention is neutral atom arrays, or as they call it, Rydberg atom arrays. So here, as you will see, the native Hamiltonian that the system realized is more like an effective spin lattice, an effective spin Hamiltonian. So again, something that is closely analog to what we are used to in condensed matter, but a different kind of Hamiltonian, right? So in particular, roughly speaking, the way it works here is that atoms are individually trapped in micro laser traps, right? That are called optical tweezers. And so basically, each of these tweezers hosts a single atom that is cooled in the local positional ground state within this microtrap. And then these microtraps can be the geometry of these microtraps can be fully reconfigurable. So you can form an arbitrary geometrical configurations of these atoms. And now the key point is that so basically you can play with a high-lying state of this atom, so-called Rydberg state. So I forgot to say these are alkali atoms, so hydrogen-like atoms with essentially a single important electrons that revolves around the nucleus. And basically, by using lasers, you can address transitions to some high-lying Rydberg state, right? And via this Rydberg state, essentially you have a sort of two-level system, and where the interactions between these two-level systems can be tuned to be extremely, extremely strong, right? So essentially, the Hamiltonian that describe the system is the following. So if you look at the first two terms, so these are two-level systems, so we can describe them as effectively as spin 1/2 particles, right? And the first two terms are nothing but the standard, atom light Hamiltonian, right? The Rabi Hamiltonian. So we have a Rabi frequency that controls the transition rate between the two levels, and some detuning of the laser that controls the energy shift between the two effective levels. And then the second part is some interaction. Yes, please. Because essentially, so you prepare these atoms in their ground state, right? And then by using lasers, you shine lasers that are almost resonant with a certain high-lying state of the atom, so a Rydberg state, as they call it, and that's why they're called Rydberg atoms. Okay, and now essentially the effective dynamics, internal dynamics of these atoms happen between these two states. Okay, so essentially you have the only states that are dynamically populated are these two states, and now the way they are dynamically populated depends on the detuning of this laser light, but also on the presence of other atoms. Because when you try, I will explain this now, when you try to excite simultaneously two atoms in this high-line Rydberg states, there is a giant interaction coming from the fact that these Rydberg states have a giant polarizability. I will come to that. So effectively, you have a spin array or spin lattice with strong spin-spin interactions that are tunable by this mechanism. So the Rydberg state is, if the Rydberg state is chosen to be, say, in the spherically symmetric series, right? So you have essentially van der Waals interactions between atoms, so interactions that decay as the 6th power of the distance, right? But the coefficient in front explodes with a high power, I think, with the 11th power of the principal quantum number. So if you address a very, very high-lying Rydberg state, the coefficient in front, so the overall strength of the interactions is giant, right? And physically, the intuition comes the following. So if you picture the atom, the micro-trapped atom in its ground state as this little blue ball, so this is like the spherically symmetric wave function of the outer electron in the atom, right? Then the Rydberg state is essentially a giant ball, right? And therefore, imagine when the atoms are sufficiently close, right, such that the physical size of the wave function of the electron becomes comparable with the distances between the two atoms, it becomes extremely difficult to simultaneously excite both atoms. So basically, the energy for simultaneously exciting two atoms becomes very high when the two atoms come close. So this is plot of the interaction energy as a function of the distance. So when the atoms are far away, essentially you can excite them to the Rydberg state independently, but when they come together, the energy for having both of them excited is so energetically penalized that it becomes essentially blockaded, as they say. So there is this phenomenon of Rydberg blockade, and this is now an entangling mechanism, because if the atoms are so strongly interacting, essentially when we try to excite both of them to the Rydberg state, effectively what we are preparing is a superposition of the left atom excited and the right one not excited, plus vice versa. So we are creating essentially a bell pair. And this was proposed as a mechanism to realize entangling gates and to realize quantum computation. But if we view this as an analog mode of functioning for our atomic system, we have effectively strong Ising type interactions between these two-level systems. So effectively, we have a quantum Ising Hamiltonian with tunable interaction strength and tunable fields, which is described by this. And I don't know if it's moving, yes. Basically, this is just to show the impressive level of control that they have. So this is a movie realized by Michel Lugin group in Harvard, where they show that they can rearrange the atomic configuration in real time, right? This is, of course, thought to be important. So, okay, here, for their amusement, they created these old video games, but The point is that the ability to bring these atoms together and to perform, to increase the interactions between them and to perform entangling gates is supposed to be key for the realization of quantum computing strategies. Okay, now just keep in mind it for later. So, and of course, there is also some more level of control. For example, we can create, we can modulate the fields acting on these atoms. For example, we can have an alternating component of this detuning, right? So this is, again, just by manipulating lasers properly, we can realize some pattern of these fields, essentially at no extra cost, other than some global control. Okay, so the last platform that I would like to mention is the so-called trapped ions, or trapped ion crystals. So these are basically ions now, so not neutral atoms, but ions, so charged atoms. And now essentially these charged particles are very responsive to electromagnetic fields, and electromagnetic potentials can be used to trap them in space, right? So okay, this can be done by various arrangements. So the most common or famous ones are the Paul trap or the Penning trap, respectively, with radio frequency fields or static fields. But basically, the point is that we can trap charged particle in this electromagnetic traps, and then they form essentially in their ground state. Once we cool them down in these traps, they form a regular crystal, right? And once they are trapped in this crystal, then again, similar principle to the neutral atom arrays, we can use internal levels of the atoms to essentially to encode some effective spins, some effective two-level systems. So in this case, in the case of trapped ions, these are hyperfine levels, right? And now the way these spins talk to each other, because of course we want an interacting system, an interacting Hamiltonian. So the way these two-level systems talk to each other is via the phonons of the crystal. Okay, so we have some effective spin phonon Hamiltonian, right, where the internal degrees of freedom talk to the vibrational mode of this crystal. And now if we tune the degrees of freedom to a regime where all the frequency, the internal frequencies of the spins are far detuned, so are far away from resonances associated with the normal modes of the frequency of the phonons, then we get an effective spin-only Hamiltonian, where essentially the phonons have been integrated out. And this kind of Hamiltonian is basically a programmable quantum Ising model, again, right? So we have some kind of Ising type spin-spin interactions described by this Jij matrix that couple the spin at position I to the spin at position J. Again, these spins are not real spins, are just hyperfine levels of these ions, right? But effectively, the analog mode that we realize is a sort of spin array or spin lattice, right? And then we have programmable longitudinal and transverse fields. So the model is pretty similar to the one that we get in a completely different way with neutral atoms, except that now the effective spin-spin interactions in this kind of platform tend to be long range. So essentially, they extend. So while they used to be short-ranged in the Rydberg atom array setting because of this van der Waals origin of the interactions, here essentially ultimately because of the long-range Coulomb interactions of the ions, these effective spin-spin interactions tend to be long-range. Okay, so you see that we have some examples of analog quantum simulators. So basically, highly controllable quantum many-body systems where effectively we can efficiently manipulate them in such a way that they are well screened, well isolated from environmental noise, and they essentially we can tweak their interactions and tweak their geometry and tweak their properties in such a way that they have a large degree of programmability, right? So we can exploit them to emulate other systems of interest, and eventually maybe to realize a universal quantum processor, but that is not my concern today. Good. So this is maybe a good point to take a pause. So if you have any questions, otherwise I will move on to the next part. Yeah, please. Absolutely, absolutely. Well, I hope so, because none of the current experiments can do can simulate 1,000 particles. So, so we'd better believe that we can do some interesting things with far less particles, right? No, that's a genuine question. I think that this is really an important question, right? So the question is basically, how far should we get in the control, in the scaling and the control of these devices in order to get something useful out of them, right? And this is a genuine question that many people are working on, right? So it's related. You may have heard about this quantum advantage quest, right? So okay, you can phrase it as quantum advantages in terms of pure computer science perspective, but in terms of physics perspective, the question is whether how much new physics can you access if you're able to control a device that has this scale and this time evolution window, right? Yeah. So this is very much an open research question. So basically, in the development of these devices, what people try to do is to realize interesting quantum simulations and compare them with classical simulations. And so far, as I mentioned, present day platforms, I think, roughly speaking, I think it's fair to say that they are at the boundary of classical computation. So I don't think there is a clear evidence of a quantum simulation that could not be done with classical computational resources. So it's kind of a race. No? So they sometimes claim that they have done that, but then somebody comes with a smarter classical algorithm to perform that, and then this is kind of a mutual race between the two. So of course, the general belief that eventually there will be a certain system size or a certain evolution time such that this will take over, right? So, such that this quantum simulator could not be mimicked, so could not be simulated classically, and potentially this will open up some new physics. But this is not, I don't think this has been achieved so far. But it's a question. How big should that be? I don't think anybody knows the answer. Good. Other question? Yeah, please. Mm-hmm. Sorry, I didn't get the question. What do you mean? What experiment do you have in mind? Mm-hmm. So you mean a certain type of Hamiltonians, if you can. Okay, this specific example, I don't think I have it on top of my head, but presumably, I mean, this looks like something one can try to do. So maybe it was done. I'm not aware of that. Yeah, thanks. Yeah, please. No, I don't think so. No, not at all. Yes? Of course, no. I agree that if this would be exactly solvable, there would not be much interest in that. No, this is in general not exactly solvable. So first of all, it's the range of interactions is variable. Second, there are longitudinal fields that break integrability, and also this is in principle fully disordered. So you can control each individual field. So it's really a very complicated Hamiltonian. It's not a solvable Hamiltonian. Also, okay, for trapped ions, it's natural to have a 1D array. But for example, in the case of Rydberg atoms, as this funny movie shows, you can have an arbitrary geometry. So you can place your spins on a Kagome lattice and have strong interactions. And so it's really far from being a solvable problem in general. Actually, okay, we can discuss, but yeah, I'm not sure I get the question. Yes. Yes, yes, yes. Well, well, pretty much like you would do a computer simulation. No? You prepare it, you let it go, and you measure things. And no, because this simulation could not be performed in principle. If you could reach suitable system sizes and evolution times, this thing could not be done on a classical computer. That's maybe I'm missing the point of. Mhm. Yes. I'm not sure I get the point. So a simulation is a simulation, right? So if you simulate the n-body gravitational problem with n planets, you cannot solve it exactly. You just simulate it in the computer. Solving the original problem. No. Sorry, that's maybe an important point. So imagine you could, for example, simulate the Hubbard model, right? So this is thought to be the correct Hamiltonian for electrons in cuprates. Okay. Well, the point is, in a quantum simulator, for example, you can image individual quoting analog electrons, right? This is something completely unthinkable in solid state. Right? In solid state, you just do global measurements of transport and this kind of things. No? In a quantum simulator, you can really image the wave function. You have a lot more accessibility to observables. You have more control, so you can change the value of interactions. You can change the value. So you can play with it, just like when you do a simulation in a computer, right? So this gives you a handle to learn much more on the behavior of the system than with the experiments with the natural. Of course, if you didn't have this kind of high level of control, then I agree, it would be just as obscure and inextricable than the original problem, right? No, but in general, you do have a lot of advantage. It's in the same spirit as a numerical simulation, right? So why do we even do computer simulations? Because you have full control and. All right. No, thanks for the questions. Yes. Yes. Okay, that's an interesting question. There are many things you can do. Ultimately, you don't know, right? By definition, right? Because if this cannot be done, okay, there is no other way. No, there are things you can do. For example, imagine you have a family of Hamiltonians that you can simulate, and imagine there is a point in parameter space where this Hamiltonian becomes solvable, or maybe, hopefully, non-trivially solvable. Then, okay, this is a non-trivial test for the quality of your simulation, right? So these kind of things you can try to do, but ultimately you don't know, right? There is no way to know. So there are things that you can do to validate, say to have reasonable belief that the platform is working in the way you expect. So for example, for short times, typically you can do an efficient classical simulation, right? So okay, if the thing is working well for short times, if the thing is working well even for long times in solvable limits, if the thing is working well here and there, then okay, it's reasonable to believe that this is working well. But ultimately, there is no way to check, right? But then I would ask you, what about computer simulation? How are you sure that your trajectory of the solar system is exactly? Mm-hmm. Mm-hmm. You mean comparing with experiments? Okay, no, this you can do also here, right? Yeah. No. This you can. If experiments are available, of course, you can always compare to experiments. No, I thought you meant comparing to other theoretical calculations. these are by definition not available, right? So the quantum simulation becomes interesting precisely because there is no other theoretical technique to do this calculation. Otherwise, maybe you would do that, right? So in the example I would like to give you in the last part of the talk, actually, maybe it's a good example in this respect. No? So the example is related to, well, again, the grand goal, the ideal goal is to simulate real-time quantum chromodynamics, right, QCD. Okay, so this is a strongly interacting theory. Typically, we're interested in this theory far from equilibrium, or okay, in some cases, we're interested in this theory far from equilibrium. For example, if you want to describe heavy ion collisions, right? So, okay, people believe that there is the formation of a thermal quark-gluon plasma, and then some hydrodynamic expansion, and then eventually some hadronization. These are all things that are far from being computable with traditional techniques like Feynman diagrams, right? So this is very strongly interacting. And also far from being computable with other classical simulation technique like Monte Carlo, right? So sampling, when you are far from equilibrium, your path integral is described by a complex phase, so there is no hope to cook up an efficient sampling for this problem, right? So okay, so there is no other technique, theoretical technique to simulate that. The only thing is to compare to experiments. That you have? Mm-hmm. Okay, so I'm not sure I get the question, but I mean, this looks very much like a problem that you would also have if you could do a computer simulation. Okay, then, I mean, it's not black magic, right? It's a simulation. So if the simulation is problematic, then you see what I mean, right? This also allows you to do a computation that you could not do otherwise. Then this computation may not be the end of the story. This may not be the solution to all the problems of humanity, right? But it's something that you could not do otherwise. That's the point. I don't know, but maybe we can rediscuss this particular example. Yes. Okay. So in the last part, I would like to tell you something we've been thinking about, well, in the last years and in particular recently. Okay, so this goes in the direction of simulating quantum field theory, in particular theories of fundamental interactions, in particular strongly interacting theories like QCD, ideally, right? So this looks like a formidable problem, right? Something really, really difficult to do. Why? Well, because you have essentially, well, implementing this kind of Hamiltonian in the system looks very complicated because you have all sorts of complex ingredients, right? So, for example, you have fermionic degrees of freedom, fermionic matter, and bosonic gauge fields, right? So they are interacting together. They are also interacting in a particular way that has a certain symmetry, so-called gauge symmetry, that is a local constraint on this kind of interactions. Now, we also have multiple species, so we have charge, spin, color, flavor, and so on, right? And as I said, you have these hard local constraints. So basically, your atoms or photons or electrons that you would like to control have no idea that you would like such a complicated thing. So these things are completely unknown to them somehow, right? So the question is, how do you even think about making an analog encoding of this crazy Hamiltonian in these systems that, as I argued before, they naturally implement some simple condensed matter type Hamiltonians, like simple interacting spin Hamiltonians, or models of particles jumping on a lattice, right? So something much simpler. Okay, despite that people started to think about how to do that, and of course, partly this is because the problem is extremely important in physics, right? So for example, the phase diagram of quantum chromodynamics is completely, so here you see something on the slide. This is essentially completely conjectured. So there is not a single first principle calculation that allows you to find this phase diagram. So we talk about a confined phase, a deconfined, a quark-gluon plasma, but these are all kind of, we only have indirect evidence of this behavior from Monte Carlo data in certain kinds of regimes, and also from experiment, right? So it would be very important to have somehow an ab initio technique for doing something like that, right? And this also plays a role, as I mentioned before, for cosmology, right? For the early universe, where the universe was extremely dense and extremely hot, right? And also for things like heavy ion collisions, for example, where it is believed that we recreate such extreme conditions of temperature and pressure that are mimicking somehow the early universe. Okay, so this is a very, very important and very interesting problem. Right? So it's worthwhile to think about. And as I argued, there is no other theoretical technique that can hope to do that, right? So all the Feynman diagram machinery cannot work for such strongly interacting problems. For far from equilibrium problems, there is no sampling technique, and so on and so forth. So quantum simulator represent really perhaps the only hope to have a first principle calculation for this kind of non-equilibrium quantum chromodynamics. Okay, so of course, as I said, this is a very, very complicated problem, but one has to start somewhere. So basically, there has been progress in a simpler, lower dimensional version of this problem, which is 1 + 1 dimensional quantum field theory with gauge symmetry. This is the so-called Schwinger model, right? Okay, so we have all these basic ingredients, but just in a lower dimensional space-time, right? So now, this is, of course, a much simpler problem than the full one. However, there are some analogies between phenomena that happen in this context and QCD. For example, this system has particle confinement, just like quark confinement, just like the higher dimensional QCD. Also, one can study, so this is sort of the natural setting to study problems like stream breaking, which is thought to be a fundamental ingredient in the hadronization phase of heavy ion collisions, and so on and so forth. So there is it is really a non-trivial somehow first test for quantum simulators. Okay, so this motivation being said, so how do we go about this? How do we try to implement 1 + 1 dimensional gauge theory? In particular, in this case, I consider U1 gauge theory, so essentially quantum electrodynamics in 1 + 1 dimensions with a quantum simulator. It's still a formidable problem in principle, and indeed, there is to date no single. There is no evidence that quantum simulators can simulate. Can achieve a simulation of this, even of this much simplified theory, right? So okay, the Hamiltonian that we would like to simulate looks like that. So we have these three colors for three different terms. So the first one is the mass term. It describes the mass of the fermionic particles of electrons and positrons, or quark and antiquark, right? Then we have the green part is just the electrostatic energy, so the energy of the gauge field per se, right? So it's a square of a bosonic field. And then this black term is basically the gauge invariant, the minimal coupling between fermions and bosons, so the gauge invariant interaction. So this is just the Hamiltonian of the quantum field theory, just discretized, so put on a lattice in a particular way that is called Kogut-Suskind realization. Okay, so basically we have to realize this model of interacting fermions and bosons with this particular kind of interaction. That's the goal, right? So just to gain a little bit of insight on what kind of dynamics this Hamiltonian describes. So let me start by considering the so-called the strong coupling vacuum. So basically, when we turn off the interaction, the black term, so the vacuum, the ground state of the system, is basically described by. So all the charges are in the vacuum. So basically, this chain of dots represents the states of the fermion, and they are associated with the vacuum. And these towers of levels between the dots are the gauge fields. So it's the electric field. So each of this, so this is a boson, right? And each of these towers, each of these levels, is associated with an eigenvalue of the bosonic field. Okay. So basically, when we turn on the interaction, so we act on this vacuum with this black term. Essentially, this is like, for example, when we act locally on this particular site along the chain. Basically, this interaction term creates a pair, electron-positron pair, which I denote as blue, red and blue particles, and simultaneously changes the value of the gauge field in such a way that gauge invariance is respected. So in particular, gauge invariance in this one-dimensional context is nothing but the Gauss law. So the electric field increases as we cross a positive charge and decreases as we cross a negative charge. So the derivative, so the divergence, which is the derivative in 1D, right, is equal to the charge content on the site between the two gauge fields. Okay, so basically the shape of this green line is sort of keeping track of the variation of the gauge field, of the electric field, and while the red and blue particles are associated with the charges. Okay, so we can act again on another site, and this creates another pair of particles. Now we can act with the interaction in the inner pair, right? And this annihilates the pair and simultaneously also raises the electric field. So we create a longer electric field string that connects the two particles, and so on and so forth. So this is basically the basic, the elementary somehow transitions allowed by the gauge invariant Hamiltonians. So we can create a longer electric string, and then we can create another particle pair with a even higher value of the electric field, and so on and so forth. Okay, so basically, we have to be able to encode this kind of A, Hilbert space, so degrees of freedom, and B, gauge invariant transitions or forces or interactions in the native functioning of our device, right? In such a way that this, for example, we are not allowed to create a pair of particles without simultaneously changing the value of the gauge field, because this would violate gauge invariance, for example. Okay, so how do we do that? Okay, so the first idea that we realized is essentially to realize an even simpler theory, where basically we truncate the values of the gauge field instead of having a full bosonic Hilbert space with infinitely many values, infinitely many states, right? If you truncate the value of the gauge field in such a way that you can only assume only two states, right? So you truncate these vertical towers of states to only two values, right? Then you can check that the problem maps to an effective spin 1/2 chain, right? And basically, these constraints arising from gauge invariance map precisely to the constraints arising from the Rydberg blockade in the one-dimensional Rydberg atom array that I showed before, right? So in particular, you can check that all the allowed states by gauge invariance maps to all and only the allowed configurations compatible with the Rydberg blockade. Okay, so this is quite unexpected, maybe, but this is kind of an analogy that allows you to encode the degrees of freedom of the gauge theory in the degrees of freedom of this Rydberg atom array. And in particular, once you check the matrix elements of the Hamiltonian, you see that there is a complete correspondence between the matrix elements of the Rydberg Hamiltonian and the matrix elements of the gauge theory once you do a set of identifications of the parameters that are reported here on the slide. So if you remember, this omega, delta, and delta are kind of the parameters that enter the Rydberg atom array, and you can map them exactly to the values of the gauge field, to the parameters appearing in the gauge theory Hamiltonian, right? And also the observables have a nice mapping, so you can simulate both sides of this analogy and check that actually there is a correspondence between for example, natural observables in the gauge theory are the charge density or the electric field profile, right? The electric field density. They map to expectation values of suitable spin operators in the Rydberg atom array. Okay, now this is of course exploits a huge simplification, right? Because we artificially truncated the value of the gauge field to only two values. Essentially, we took the strong coupling limit in the gauge theory, but the strong coupling limit is sort of the opposite of the continuum limit. So if we want to simulate the gauge theory in the continuum, we should be able to reach the opposite limit where the gauge field can fluctuate. On a lattice scale, the electric field can fluctuate by far, essentially. And this is kind of automatically out of this description, right? So more recently, we came up with a new idea, essentially, where you can encode the Hilbert space and the interactions of the gauge theory for arbitrarily large truncations of the gauge theory. And this is quite remarkable improvement. And I just going through the mapping would be a bit too involved for this talk. Also, we are running over time. But basically, I just want to convey the main point. So the main point is that now we use a quasi-one-dimensional strip, a quasi-one-dimensional Rydberg atom array. I told you before that these neutral atoms can be completely reconfigured in arbitrary geometry, right? So if you arrange them in this quasi-one-dimensional strip, and then essentially you can work in the regime where this Rydberg atom array maps to an antiferromagnet, right? So this checkerboard and anti-checkerboard configurations that you see in the top and the bottom part of the strip, they are basically the two antiferromagnetic states of this effective magnetic Hamiltonian, right? And the interface between this checkerboard and anti-checkerboard regions, essentially, you can check that it maps in a suitable regime, it maps one-to-one with the allowed configurations of the electric field string, right, that are compatible with gauge invariant operations in the gauge theory. So, okay, this is a bit abstract, but I think there is a remarkable point to be made here, is that originally we had a theory with fermionic degrees of freedom, bosonic degrees of freedom, and some constrained gauge invariant interactions. Now we map it essentially to a purely spin magnetic Hamiltonian, just on a larger, the price to pay is that we have now a larger Hilbert space, right? Because we have not just a one-dimensional chain, but a one-dimensional strip with a certain width. And this width is nothing but the size of the allowed electric field values that we keep in the truncation of the gauge field. So in this way, basically, with the natural dynamics, the natural native Hamiltonians of this condensed matter style spin-spin Hamiltonian, we realize, quite unexpectedly maybe, we realize this kind of gauge invariant interactions in 1+1 dimensions. And now, so okay, I sort of swiped all the details under the rug, but the main point here is the ability to have global control on this detuning field. So basically, the claim is that there is a suitable detuning laser pattern that allows you to map exactly the Hamiltonian for this interface in the magnetic system to the Hamiltonian that governs the dynamics, the gauge invariant dynamics of fermions and bosons in the gauge field. That's just the claim. Of course, I didn't go through the proof of this claim, but yeah, all the details are discussed in our article. And now, of course, there is another detail that I swiped under the rug, the fact that these Rydberg atoms have some longer range interactions, right? So these longer range interactions are sort of giving you unwanted terms in the realization of the gauge theory. Now, basically what you can show is that if you use a dual species setup where the red and blue atoms that are on the even and odd sides of the lattice, they have different species, essentially by controlling intraspecies and interspecies interactions, which has been shown experimentally in this realization of these neutral atom array platforms. This allows you to kill these unwanted terms. So you really realize the Schwinger model Hamiltonian. Okay, and okay, maybe I should, I don't know if I should cut. Oh, still 5 minutes. Okay, so I can basically, I can just quickly flash what is one probably interesting application of this approach is to simulate collisions, right? Collisions or the stream breaking problem. So okay, the simplest to explain is maybe the collision where you have essentially bound states of quark-antiquark or electron and positron. You want to be able to prepare them in a suitable incoming wave packet with certain momenta, let them scatter and see what happens, right? So in principle, out of the collisions, you can come out with a distribution of bound states of particles, right? In this, so I told you that this one-dimensional gauge theory has the property of core confinement. So you only have bound states in the spectrum, but the distribution of the bound states are emerging from the collision is in principle unknown and is a completely non-perturbative calculation in principle, right? So basically, what we have shown is that you can do this. You can do some engineering to encode this particular initial state that is a peculiar initial state with certain sharp wave packets you can do some suitable state preparation that is available with present-day sort of the toolbox in this platforms, and you can actually realize this, right? So both the state preparation and the detection, so the measurements of the relevant observables. This is for Rydberg atom arrays, but actually we have also worked on the realization of this protocol in the context of trapped ions more recently. And here you can really tune the properties of the Hamiltonian, for example, across a deconfinement transition, and check that out of the collision you can deconfine the quarks if you work in the deconfined phase of the model. Okay, so this is just a very quick flash, just to give you a flavor of the kind of baby steps that one can take in this approach, and that we believe eventually will lead to really getting some non-trivial insights that can be useful for phenomenological models that people use to fit data in particle colliders, for example. Okay, this is all. So thanks for listening.
Question round, but perhaps there's a couple of simple questions still. Yeah, that would be great.
I have maybe a difficult question.
Mm-hmm.
No, actually, since you're working now in Leuven, there's a lot of string theories around, so I was wondering if you want to simulate string theory as well, so can you imagine a string theory simulated as well?
Yeah, that's an interesting question. So. My knee-jerk reaction is that it's already challenging. You know, we are struggling to simulate 1 + 1 dimensional quantum field theory. So probably 26-dimensional quantum field theory is a bit far-fetched. But yeah, no, I mean, who knows, right? I would tend to think that this is kind of the opposite approach, right? Because essentially here we start from something extremely well-defined that we discretize, we put on a lattice, pretty much like people do in lattice QCD approaches, right, where they compute, for example, the spectrum of the lightest hadrons by sampling techniques on imaginary time QCD, right? So essentially, you should view this approach as an approach to do lattice QCD calculations just in far from equilibrium, so in real time rather than in imaginary time, and at finite density of particles. So these are both regimes. So these two axes are out of reach for Monte Carlo techniques, right? So, and here I think quantum simulation techniques can have some strengths against other approaches. Of course, probably we will never be able to simulate actual QCD. I think that's, you know, some simple estimates tell you that this is maybe out of reach on our lifetime, I would say. You know, because it's a very complicated Hamiltonian, but maybe you don't really need to put 6 flavors of quarks there. So maybe, you know, some simpler versions of this model can maybe give you some insights. Now, given that this is so difficult for this for QCD, now, yeah, okay, I haven't really thought about it, but I would be extremely cautious about making claims on simulating even more complicated Hamiltonians. I don't even know if they have a Hamiltonian, actually.
I have a very stupid question, okay?
Okay, no.
Start with one, and also give...
Yeah, a very stupid question, actually. Because I was listening to Davis, CEO of DeepMind.
Sorry, to chemists?
Davis, CEO of DeepMind.
Okay.
This show results for 2 different cases, one for AlphaGo and another for protein calling. Initially, we thought that we require quantum computer because the number of steps are really large.
Yes.
And for both, they use a classical computer, AlphaGo. And what you were saying is that because the universe is going to several equations, and most of the things that we are interested in have structure. And if there is structure in your problem, AI or classical computer is good enough for that. So results for AlphaGo and protein calling. Because there are infinite systems. So the question is then why we need to go quantum systems?
No, that's a perfectly valid question, I think. So, okay, so I try to emphasize across the talk that I was always talking about brute force simulations, right? So what does it mean, brute force? That we are not trying to take advantage of any feature, right? Of course, there are certain problems that don't need, where clearly we can efficiently simulate. Some other problems that we can less clearly, but this is probably achievable, that one can classically simulate them with polynomial efficiency. I also work on classical computational strategies, so I also do that. Now, the question is every possible interest in quantum evolution classically simulatable? I think almost everybody believes that the answer is no, right? Okay, trivially, if you think about Shor's factoring algorithm, that is a particular quantum evolution, quite structured. And okay, if you could simulate that efficiently classically, this means that you could factor large numbers in polynomial time. And okay, this is no proof, but essentially everybody believes that this is not the case, right? Even though it's not proved. Now, question is it the only problem that is provable, provably, or almost provably out of reach for classical computers? I think it's very natural to believe that this is not the only problem. So I think far from equilibrium dynamics of QCD is likely out of reach for classical computer, although there is no proof, right? So I would tend to think that non-equilibrium interacting quantum dynamics is generically a problem that is out of reach for classical computers, although no, I cannot prove it for you, right? Now the question is, can you distill a particular problem where you can actually show that this can be done and this cannot be done in the other way? This is still an open question. I think there is a lot of reasonable belief that this is the case, but the question is open, right? So there are classical simulation strategies are improving, quantum simulation strategies are improving, and
It's not about simulation. It's about determining structure.
yes.
That the source of this space is much lower dimension than the original space.
Right, but
So to take this discussion, the reception, I think Michiel had one question.
Also quite general. So when I try to explain to layman people what can be the benefits of quantum computing, I think chemistry is one of the major ones. So do you see any time scale on which
no, I think it's hard. I think everybody who give an answer to this question is lying, right? So it's. I mean, it very much depends on experimental progress, so it's hard to predict, right? So some people even claim that there will be fundamental bottlenecks, right, along the way to scalability, right? So I think it's really genuinely not. I think it's hard to make any predictions. What can be done is extrapolating from, in 1995, I think people managed to trap a single ion and observe Rabi oscillations of a single ion. This was a stunning result, right? Now, 30 years later, we have systems of hundreds, the ballpark of hundreds of ions, and with provably controllable non-trivial interacting simulations of this. So, okay, there is a clear progress, right? But then what happens in the future, it's hard. Okay, in the field of chemistry, it's not my domain of expertise, so I'm not sure. Like for QCD, for example, I think easy estimates tell you that you need such a high number of such a big system that is probably we will never see this, right? Yeah, something like that. So this is that's why I said before, I don't think quantum simulators or quantum computers will be able really to perform such simulations. But what I think will be the case is that you can distill simpler problems, right? So for example, the problem of stream breaking in a lower dimensional but still confined in gauge theory, right? And what we can learn from this simulation can be used as an input for phenomenological models that fit data, right? Because at the moment these are purely phenomenological, right? But if you learn some of this, for example, fragmentation functions from ab initio computations on simpler models, this can be beneficial. So I think this is reasonable, and probably we will see this in our future. Now, a fundamentalist approach to the problem probably is too much, I think, but who knows? I mean.
Thank you all for the interesting questions. Thank you, Alessio.
Thank you.